Hi guys, in this video we're going to start talking about nuclear radiation. This is a branch of chemistry where we're talking about the inside of the atom. More often than not, chemists really are more concerned with the atom as a whole and how it interacts with other atoms, and so nuclear radiation is usually a part of physics because physicists are a little bit more concerned with what's going on inside. So let's get ready to talk about it. We've got some handy Cornell paper here that we're going to be using. And your name and class period would go over here. Today we're going to be talking, this is Unit 9B, Objective 1, and our topic is just kind of an intro to radiation. We're talking about what is radiation, and so we're going to be answering a couple of questions. Our first question that we're going to answer is, what is radioactivity? And the second question we're going to answer is a little bit about how it's measured. How is radioactivity measured? And there's several different things that we can measure, and we'll talk about those things. So first we're going to go through a brief history of radioactivity. And I'm going to write radiation here. History of radiation. Okay, so a long time ago, 1895. We're talking, this stuff has really been around for a good long time. In fact, it's been around forever. Forever, radiation has been there. We just only more recently noticed it. In fact, it was 1895, this guy named Röntgen, who has he's German, he discovered that some X-rays, were X-rays made in a cathode ray tube. We learned about a cathode ray tube before. That's how Thomson figured out that electrons had charge. It just shoots these things, and Röntgen found that X-rays were able to come out of it. And imagine how excited he was when he shined it through his hand onto some paper and could see his bones. Just imagine the first time that anybody was ever able to see the bones inside their hand without being dead first. Some time went by, like a year, and this other guy named Henry Becquerel, with a Q, he noticed that those X-rays, some of that radiation that they were looking at, turns out some of those X-rays are a little bit more energetic, and then they start to become called gamma rays. But this guy Becquerel, he saw that radiation came from materials on their own. So he was doing this experiment where he had some uranium, and he thought that the sun shined on it and then later it would let radiation off. But then when he was doing his experiments one day, it was cloudy and he couldn't do any more experiments, but he still got stuff to come off of it. And so it turns out it was coming out of the uranium and not from the sun like they originally thought. So that was when they first decided or discovered that radiation came from things naturally. So then move forward, and maybe you've heard of this woman, Marie Curie. She's got a husband, Pierre Curie. They worked together, but Marie Curie was the one who was interested in it. She was just interested in what Becquerel was doing, and so she did some research, and she found other substances that emitted radiation. And she was the one who coined the term radioactive. So radioactive is the term that we use to describe things that emit this radiation. If it emits that radiation naturally, we call it radioactive. And then the next question is, why? Why are some things radioactive? Alright, so we're going to take a look here. This is going to look a little bit like Physics 9. Remember good old Physics 9? Here's a proton, and here's another proton. Do protons like each other? No. So there's a force pushing this proton away, and a force pushing this proton away. And I'm going to call that force proton. This one's force proton too. Now there's another force on these guys, and that is usually thanks to some neutrons that are nearby. But there's another force, and it's called the strong force, the strong nuclear force. Well, this is just both of them. So there's this tug-of-war inside the nucleus where the strong force is pulling those things together, and their own electrical forces are pushing them apart, just like static electricity. And so when those forces are balanced, then the nucleus just kind of stays together. If the strong force, if it wins, then you have a stable atom. Okay? If the strong force is bigger, then that atom stays together, the nucleus sticks together like glue. But if that proton force, if that electrical force wins, then you have something that is unstable. So we're still getting a better understanding ourselves of how all this works. One thing we do know is that we can't predict which ones will and which ones won't break down. That there's just it's a flip of a coin. Somebody's constantly flipping a coin, waiting for it to come heads up. Some atoms flip their coin heads up faster than others, but that's pretty much it. So basically, it is an energy or a force imbalance. If there's an imbalance, that causes the atoms to break down. And we call them unstable, and the word we use when they break down is decay. We say that they decay, and they turn into a bunch of other things. So one more thing about what is radioactivity, and that I'm going to put on the back side here. There are three main types of radiation. That is nuclear radiation. I'm going to write that up here, nuclear radiation. There's all kinds of radiation, but there's only three types of nuclear radiation. Three main types, and that is alpha, beta, and gamma. Remember that guy Rutherford who shot some alpha particles at some gold foil and they went through? Surprise, surprise. Rutherford is the one who gave these guys their name, alpha, beta, and gamma. You can learn more about alpha, beta, and gamma in the next video, which is types of radiation, where we'll talk explicitly about those things right there. So then our second question, that is our essential question, is how do we measure it? How do we measure radiation? And there's a bunch of different ways. The first thing that one of the things that we can measure is something called a half-life, which there will be more on this in Objective 3. So I'm going to write that here. I'm just going to define it here. A half-life is the time it takes for half of a radioactive sample to decay, and that's something really super special, and we'll talk more about that there. But basically the idea is if you have all these radioactive atoms, some of them will become not radioactive and some of them will stay. And the time that it takes to get to half of them no longer being radioactive, that's what we call a half-life. Okay. Now some other measurements that we can do, we measure the radioactivity. Is actually measured in a Curie. It's named after Madame Curie there. And what it is, it's how many decays per second. Okay, so if you have a sample of atoms, how many of them are decaying each second, that would be the radioactivity that we'd measure, and we'd measure that in a Curie. Now, when it comes to effects on people, we can measure a couple of things. We can measure the radioactivity, but what we really care about when it comes to people, in relation to people, we are more concerned with something called dose. Just like a dose of medicine, we're going to talk about dose of radiation. So, and your dose of radiation is essentially how many of those decays are going through your body, and it's measured in something called a REM, R-E-M, and I have no idea what that's short for. I think I used to know, but it measures how much radiation you're actually being exposed to. So imagine this. So let's pretend this is our radioactive sample. We'll just draw some stuff coming off of it. There it is. Okay. Now you're here, and there's another guy over here who's getting a bigger dose. This guy, higher dose. Okay. So dose depends on how far away you are. If you're getting a lower dose, more of it's going away from you because you're farther away. Now, the other way you can change your dose is by staying there. So let's say, here's our second example. This is here. Okay, so maybe this guy stands here for 5 minutes, and this guy stands here for 20 minutes. This guy's going to get a lower dose because he's exposed to it for less time, and this guy's going to get a higher dose because he's exposed to it for more time. And it's the dose that matters more than the radioactivity, because if something is really radioactive but you're only there for a second, then you're going to get a lower dose than if you have something that is not very radioactive, but you keep it in your pocket for a year. So it's the dose that matters when it comes to radiation, not the exposure itself. So we'll learn some more about those things in some other videos in the future. Now you can go answer some questions about this in your homework. Thanks for watching.